Welcome to lesson 24 of the Advanced Higher Stats course. In this lesson, we'll be looking at chi-squared tests. At the end of this lesson, you should be able to do a one-tailed chi-squared test. An overview of this test. This test tests if discrete categories of data are associated. So like if a drug can affect the outcome of a condition, that would be an association. So because of that, the null hypothesis is normally no association. The alternative hypothesis is that there is an association. Some criteria here, we will be working with expected frequencies. And when we do calculate them, we want all of them to be above 1, and we want 80% of them to be above 5. On the data booklet, it says look at page 6, and this is what we get. So we will be using this formula to be finding our test statistic. And when we find our critical value, we will need the degrees of freedom, and this is how we get it. And this is an example of what a conclusion would look like. Let's jump straight into it. Two groups of patients suffering from the same medical condition took part in a clinical trial of a new drug. One of the groups was given the drug, whilst the other group was given a placebo, a drug that has no physical effect on their medical condition. The tablet shows the number of patients in each group and whether or not their condition improved. Conduct a chi-square test at 5% level of significance to determine whether the condition of the patients at the conclusion of the trial is associated with the treatment they were given. So first thing we do is we write the null hypothesis, which is condition is independent of treatment, so treatment does not affect the condition. An alternative is that condition is dependent upon treatment. Okay, now what we need to do is calculate the expected frequencies and then relate them with the ones we've observed. And how we do that, something we have to do before that is we have to add up the rows and columns. So we will have 66 here, we have 75 here, 75 here, and 84 here. And in total, that gives us 150. Now to find expected frequencies, if I draw the same table here, what we have to do, we have to times the column total, which is 75, and then times that with the row column, which is 66, over the total, which is 150. And that gives us 33. So we would put 33 here, because for the placebo and condition improved number, row total is 66, column is 75, total is 150, and we do the calculation and we get 33. Now we do that for all the boxes. So this time we do 75 times 84 over 150, which gives us 42. So we can put 42 here. And for this particular scenario, we do the same calculations for the other two boxes. The answers will be the same. So we have our expected frequency, and now we have our observed frequency. Now we need to find our test statistic value, and before that, we have to find our degrees of freedom. So how do we find our degrees of freedom? We do the number of rows minus 1 times the number of columns minus 1. So rows minus 1 times columns minus 1, which is 2 minus 1 times 2 minus 1, which gives us 1. It's at 5% significance. So our chi-squared critical value is 3.841. Now we need to find our test statistic value. And how we do that is for every observed value, we take away the expected value. So what I mean by that is 20, which is our observed value, minus 33, which is expected value, all squared over the expected value. And then we do that for each observed and expected value, and then we add them up to see if it's greater than a critical value. Now, before I do that for every number, I want some of you may have noticed that if you compare the expected values with observed ones, there's always a difference of 13. So you have 20 here, you have 33, the difference is 13. 46 here, 33 here, difference of 13. 29, 42, difference of 13. 55, 42, difference of 13. So to speed this up, what you could do is you could just do 13 squared, or even just 169 over each expected value added together. So 169 over 33 plus 169 over 33 plus 169 over 42 plus 169 over 42. And that gives us 18.29. And since 18.29 is greater than a critical value, which is 3.841, you would reject H naught and you would say something like there is evidence to suggest that the condition of patients may be dependent upon the treatment that they have received. Let's do another example. At the end of the first term at university, the same stats exam was taken by both psychology and biology students who had been taught by different lecturers. The frequencies of grades awarded to a random sample of students are shown below. As part of their calculations, the research student had correctly generated the expected frequencies to be those shown below. State an assumption, then test at 10% significance level to see if stats grades are independent of core subject. Okay, so our assumption here can be that the lecturers were the same level of have the same level of skill in teaching. That not one lecturer isn't better than the other at teaching stats. That would be our assumption. Our hypothesis would be stats grades are independent of core subject. And what we're trying to prove or test is that stats grades are dependent on course subject. Okay, now before we move any further, we should see that the expected frequency table meets our criteria, which was that every expected value should be above 1, which it is, and 80% of those expected values should be above 5. Now we have 10 expected values, and 4 of them are not above 5. That's 40%. That's too much. And how we do that, and how we fix that, is by collapsing columns. And that just means combining 2 columns together. So we will combine D and E. So we make a new column, and you would add the values in D and E. So here we would have 9.2, and here we would have 5.8. And we would just kind of ignore this column now. And now we can find the degrees of freedom, and it's important to find the test statistic value after you collapse columns. So it's rows, the degrees of freedom is rows minus 1, which is 1, and times columns minus 1, which is 3, which gives us 3. Now we look at 10% significance, which is here. Degrees of freedom is 3, so that is 6.251. So our chi-squared critical value, that is a awful chi-squared symbol, chi-squared critical value is 6.251. Now we can go on to find our test statistic. But before we find our test statistic, we also have to combine the D and E columns on the observed value or the observed table. So we would do D slash E, and we add these together, so we get 6 here and 10 instead of these other numbers. Now, what we can't do here, we can't use that trick I showed you in the previous question. That is because this table is not a 2 by 2, it's a 4 by 2. So the trick doesn't apply. You see, if we look at the difference between 13 and 10.4, it's 1.6. But if we look at the difference between 6 and 9.2, that's 3.2. And the difference between 6 here and 7.3 is 1.3. So we have to individually do the formula, which is observed minus expected, all squared over expected. And we do that for every single box. And I'm not going to do that here because the video will get really long. But what you should end up with, the value you should get should be 6.055. Now that is smaller than a critical value. So you would not reject H naught. So say not enough evidence to reject H naught and conclude stats grade is dependent on course subject. So the main step here I'm going to teach you for this question was the collapsing columns. Everything else was the same as last question. Now you should be able to do a chi-square test.